So in the last lesson was the first time that we had looked at resultant vectors, and we did resultant force. Okay, and so that we're talking about how many, pounds of force or whatever we had. But this is velocity, so we're going to be talking about speed as our magnitude. So your magnitude could be a lot of different things, but last time it was force, this time it is velocity or speed. So it's about the same. It's the same concept, but we're going to draw the vectors out a little bit differently so you can actually see better how they're being added and what's happening. So we have an airplane so our airplane is traveling at a speed of 500 miles per hour at a bearing, that's important, of 325 degrees. Once the airplane reaches a certain point, it encounters a wind velocity of 60 miles per hour in the direction of north 75 degrees west. And then we're going to find the resultant speed and direction as a true bearing. So we're given one as a true bearing, one is a quadrant bearing, but our answer has to be in a true bearing. Okay? So let's see. We're going 325 degrees. So up here. So we'll say, all right, we've got our plane is flying at a bearing of 325 degrees. So that would start here, go all the way around. So it's about like, oh my goodness. It's about like this. Okay. And this right here is 325 degrees. And this is 500 miles per hour. Right. So what we need from this is we need theta. Theta goes from here to here. And I've worked way more of these problems than y'all ever have, and I don't trust myself to find these without sketching out a picture and drawing it, because otherwise you're going to get confused about what you're adding and subtracting. Okay, so there's more than one way to actually get to theta, but what do you think one way would be? Okay. Okay, good. So if I went here all the way around, that's 360. So if I subtract that 325, I'm going to get 35 degrees for this little piece right here. And then I can just add that to 90. So that's going to give me 125 degrees. Okay, we agree with that? So that's this theta that goes with the airplane. So I'm going to come over here and I'm going to mark out this 325 because it's 125 that I'm actually using. Because last period we did all this, but then when I was writing it, I went up here and I grabbed this number and then I grabbed 325, and of course they let me finish most of the problem before anybody said anything. So not a bad idea to cross them out. Okay, so when we're adding vectors, we have this one vector, and then we add the other one starting where this one ends. So we'll have, let's see, wind velocity of 60 miles per hour, north 75 degrees west. So north 75 degrees west. It's like this. No, that's not good. North 75 degrees west is like this. Okay. So this right here is 75. I need theta. What am I going to do to get theta? Add 90. So my theta here then, theta is 165 degrees. So I'll mark that out and put 165. So my resultant vector goes from here to here. And it's not super to scale. That's why I had to redraw this one, because it was almost like it was at a straight line because my scaling isn't that great. But you get the idea of where the vector would be. Okay, see what's happening there? Okay. All right. So now we're going to make our little vectors here. And we have the plane. So we'll do P for plane. So the vector that is the airplane, we have a speed of, that's our magnitude, 500 times the cosine of 125, and then 500 times the sine of 125. Then we have the wind. So our vector for our wind is 60 times the cosine of 165, and 60 times the sine of 165. So now that we have each vector written, what do we do with them? Add them together and do what in the calculator? Save them. Yes, so add them together and store them. I would just store them in A and B. But make sure that you store them. When I was making the key to the review and the test, I worked the test multiple times because I felt like it was too long, so I kept cutting things and reworking it. But then I was comparing my answers. I didn't get the same answer on one question, and I realized it was because I did all the stuff right, but I accidentally didn't save the second one, so it was using the answer from the one before. So once you get them, you store them and write them down, and I'll write down what you should be getting. But then it's not a bad idea just to hit clear and do recall A and recall B and double check yourself if you're worried about not accidentally not saving them. Everybody good at this point? Okay, so what's your question? Make sure you close your parentheses on those first angles. Okay, so now that we have this, what quadrant is this in? Or what quadrant are we dealing with? 2. So this is in the second quadrant. Oh. Okay, so now we need to find the resultant speed. So that's our magnitude. So the magnitude of my resultant vector, that is the square root of a squared plus b squared. You can just do that in the calculator. But of course, you're not going to get the right answer if you didn't store them. I'll give you what you should get. Make sure this is what you're getting out of your calculator. And what would the units be on this? Miles per hour, because it's the resultant magnitude or the resultant speed, so it is the same units that the originals have. And remember, in formative, you're leaving off the miles per hour, but on your paper, on your review, on your test, make sure you're actually putting those things on there, okay? Everybody good with that? Okay, so now I need to find theta. Theta is the tangent inverse of b over a. So I need first to get alpha out of the calculator. Let's go ahead and find that. What do you get for alpha? 50.959. But is that what your calculator says? No, your calculator says negative, right? So what do you do with that? Multiply by -1. So we can keep everything with alpha, and then everything you have is consistent, okay? So that's alpha. I'm in quadrant 2. What do I do with alpha to get theta? Subtract from 180, and that would give you that 129.041. But then I'm going to double check up here. I need it as a true bearing. So as a true bearing, I'm going to kind of sketch out where my angle is here. I'm in the second quadrant, so this is my 129 degrees. What do I do with that to get my true bearing? And my true bearing would go from here to here. Again, you have a couple of options. Okay, I can subtract 90 from this 129. That'll give me this right here, which is like 39 something, right? And then what do you do with that 39 something? Subtract it from 360. That totally works. Okay, so let's write that answer down, and then we'll talk about another option. One's not better than the other. It's just a different way to look at it. So your beta then is 329 I'm sorry, not 320, 320.959 degrees. And the calculator is just doing all, just keep the exact answer in there and let it, subtract the different ways. Questions? What's your question? So this is 129. I subtracted this 90 to get this piece right here, which is 39 something. And then I subtracted that from 360 to get that right there. Okay. Another option would be to take 180 and subtract 129, and that right here would give you that 50 something. And then you could take 270 plus the 50 and you get the same answer. Again, one's not better than the other. It's however you see it. And if you remember in geometry, when you had circles that look like this and they'd have a bunch of angles on there, they'd ask you for this angle, this arc, and you had it. That's one reason why you're doing that, because it's the same kind of thing, and you just reason your way around it, whatever way makes the most sense. Okay? All right, what questions do you have? All right, good deal. All right, let's look at number 11. So I'm going to start here. So a baseball player runs forward at 15 feet per second. So here's my baseball player running forward at 15 feet per second. Then he throws a baseball. Well, and not then he throws a baseball. It's not like he's going to run and stop and then throw. But the way the vectors look, the vectors aren't necessarily an actual depiction of what's happening. It's just how you add vectors. So this is one vector. He throws at 80 feet per second at an angle of 20 degrees. So this is 80, and this right here is 20 degrees. So my resultant vector looks like this. Okay. Does that make sense? So now that I've kind of drawn that out, my 15 feet per second here, what's the angle for the baseball player? 0. You got it on the coordinate plane right here. Isn't this 0? That's 0. Okay. And then we've got 80 feet per second at an angle of 20 degrees. So then I want, what is the resultant speed and direction of the throw? So it doesn't ask me for a quadrant bearing, because that really wouldn't make sense when you're throwing a baseball. If it doesn't say anything, then it just has to do with the horizontal. It'll just be theta, basically, in the end. All right, so let's write these out. We've got, so we'll have the player. We'll do P for player. That is going to be 15 times the cosine of 0, 15 times the sine of 0. Then we have the baseball. That's going to be 80 times the cosine of 20, 80 times the sine of 20. And then let's talk about something else before we start pushing buttons on the calculator. What is the cosine of 0? 1. So 15 times 1 is just 15. What's the sine of 0? 0. So 0 times 15 is just 0. So I have simplified this vector to this right here. So when I'm typing it in the calculator, I don't have to type all this mess. I can just do 15 times this right here. 15 plus this right here to get my x component, and then my y component is what it is when we add them together. This gives me less. Now, of course, it's fine to type this stuff in, especially if you don't trust yourself, but if it's something's obvious to you, you can definitely simplify it along the way. So go ahead and type those in and store them. I'll give you a second to do that, but I'll write up here what you should be getting. In this resultant vector, what quadrant? First, okay. And even though my drawing is clearly not to scale, I still can see my resultant vector. The fact that it's the first quadrant vector does totally make sense, so that's a good thing. let's go ahead and find the magnitude. So the fact that he's running when he throws it helps with that velocity, right? Then theta, we know that that's the tangent inverse of b over a. And since this is a first quadrant angle, and I don't have to do any kind of bearing stuff, then what the calculator gives me is theta. And theta is 16.879 degrees. And even though, again, clearly not to scale, because this does not look like a 16-degree angle. It looks more like a 45-degree angle, right? But you can tell that it's less than the 20, right? So even though my 20 doesn't look like 20, my other angle has to be less than that, so we're good. Okay? What questions do you have? Alrighty. Let's try another one. All right, so we have a boat that heads directly across the river with a velocity of 28 miles an hour. So a boat directly across 28 miles an hour. The river is flowing at 12 miles per hour. Find the magnitude and direction with respect to the shore. Okay, so here's my river. Right? So this boat is going to go directly across the river. The velocity is 28 miles per hour. But the river is flowing at 12 miles per hour. Right? So when I add those two vectors together, tip to tail, then this is my resultant vector. So it's kind of like if you have a flowy river and you're trying to get directly across, and no matter how much you try and aim to that, if you're going straight across, the river's going to carry you down, right? It's like when you're in the ocean at the beach and you think you're standing in the same place because you're not really swimming or anything, then you turn around and all your stuff's like way down there because the current carried you. Same idea here. So it's like, how much does this current affect my speed and the angle that I went at, right? Okay, so the boat, from my little picture here, went directly across the river. What's the angle for the boat? 90. Good. And then what's the angle for the river? 0. Okay. And then I want it with respect to the shore. So basically it's like the shore is the x-axis. So the angle that I want right here is just going to be theta. Okay. So let's write these out. So we have the boat vector. That's going to be 28 times the cosine of 90. 28 times the sine of 90. Then we have the river. It's going to be 12 times the cosine of 0, 12 times the sine of 0. So let's simplify these before we go to the calculator. What is the cosine of 90? 0. So that means that this x component is 0. What's the sine of 90? 1. So this is 28. The cosine of 0 is 1, so that makes this 12. The sine of 0 is 0, so that makes this 0. So adding these vectors is super easy. Don't need the calculator at all. It's 12, 28. So then to find the magnitude of the resultant vector, that is the square root of 12 squared plus 28 squared. And what's 12? What is that then? 4 square root of 58? Oh, and what are the units here? Miles per hour. Any questions? All right, so theta is the tangent inverse of 28 over 12. And this is a first quadrant vector, but we kind of had already decided that whatever theta is, it is what it is. And you should get 66.801 degrees. So remember, units, important on the paper and stuff. Don't worry about typing them into formative. Any questions at all? So I don't think this part right here really is an issue for you anymore, but getting the correct angles to go with in the first place and then maybe handling the angle at the end is something that you need to focus on. All right, let's try one more. A drone is flying at a speed of 40 miles per hour in the direction of south 70 degrees west. There is a wind of 15 miles per hour in the direction of south 10 degrees east. Okay, so find the resultant magnitude and direction as a quadrant bearing of the drone. All right, so we're going to start here. We're going to go south 70 degrees west. So this right here is 70 degrees. I need theta. So to find theta here, what could I do to find theta? Or what is theta? Yeah, 200. You were going to answer the first question, then you answer the second question. Yeah, so it's 180 plus 20, because if I do 90 minus 7, there's 20, so 180 plus 20, that's going to give me 200. Or I could do 270 minus 70. It doesn't matter either way, but you get 200 degrees. So I'm going to come over here, I'm going to mark that out, and change that to 200 so I don't do something ridiculous. All right, so then I'm going to add to that another vector. And this vector says it's going 15 miles per hour in the direction of south 10 degrees east. It looks something like this. This right here is 10 degrees. I need theta. What's theta going to be? 280, because if this part's 10, I can just do 270 plus 10, so it's 280. So I'm going to mark this out and make that 280. So then my resultant vector is right here. So I already know by drawing that out so I can find my angles and actually adding them together instead of doing two separate ones like we were. I didn't want to put them all together too quickly. That I can see that I'm pretty confident, even though it's not to scale, that I'm going to have a third quadrant vector. Right? It's what my picture looks like, even though it's not to scale. I think we're good. All right, so let's write these out then. So I'm going to start with the drone. It is 40 times the cosine of 200, 40 times the sine of 200. And once again, make sure that the only difference between your x and y components is the cosine and sine. You're not mixing things around. Then we have wind, and that's going to be 15 times the cosine of 280, 15 times the sine of 280. And those aren't special angles, so just type all this stuff in again. I'll write the resultant up here, and then I'll give you a minute. You go ahead and find the magnitude. After you double check that your resultant's correct and you actually have it stored in there, then you find the magnitude and the quadrant bearing. Then I'll talk you through it. I'm sorry, what? Yes. That's good so far. See if you can do that part. You're not wrong, just not finished. South to, yeah. Well, you either go north or south and then east or west. Yeah. So it's not wrong, just not finished. You doing okay? So the quadrant bearing is when you go like south and then east or west. So I would draw that out so you can figure out which direction you're going to go. Are there any questions about the magnitude? I feel like if there's going to be any, it's going to be about the angles. So are we all good with the magnitude? All right, so let's talk through the angles. So I'm going to take the tangent inverse of b over a. So I'm going to get 39.123 for alpha. But this is, I need a quadrant 3 angle. So if I have alpha and I need quadrant 3, I just add that to 180, right? So this is going to give me 219.123. So that angle then is like right here. That's 219 degrees. I need this as a quadrant bearing, which means I actually need this part. So I can say I'm going south, something west. So a couple different ways I could get this. I could take this, because if this is 180, this is that 39 part, and I could subtract that from 90, or I could take 270 and subtract that 219. Either way, I'm going to get south 50.877 degrees west. One way is not better than the other. It's whatever makes the most sense to you. It's, manipulating the numbers in the calculator. Any questions at all? We all good? Ask me a question. All right. So now let's talk about horizontal and vertical components. So a vector can be resolved into horizontal component and a vertical component. The horizontal and vertical components are also called the rectangular components. Because the rectangular components form a right triangle, you can use trigonometric ratios to find their magnitudes. Okay? So Danica's pulling a sled with a force of 400 newtons using a string. So she's not like crouched down on the ground pulling the sled itself. She's pulling it with a string. The sled's on the ground, right? And it says the string makes a 35-degree angle with the ground. So she's pulling, here's the string. Okay, this is 400 newtons. Here's the ground. It makes a 35-degree angle with the ground. We want to find the magnitudes of the horizontal and vertical components. One, it says it forms a right triangle. So here is my right triangle. My horizontal component is x, my vertical component is y. Now, I drew the triangle this way. We don't know which direction she's pulling, So she could be pulling it in this direction, right? Oh, well, it should look semi the same. Hang on. Illustrate my point here. It'd be better if my picture's better. She could be pulling in that direction. So like this vector would have a negative x and a positive y component. This one would have a positive x and a positive y, right? But we don't know which direction she's pulling in. So how I draw my triangle really doesn't matter. In the end, my components are just going to be the positive version anyway. So we're just going to use the absolute value of x. So to find x, right, we've got a right triangle. It says we can use trig ratios. If this is my angle, this is adjacent, this is hypotenuse. Which trig ratio uses that? Adjacent and hypotenuse. SOHCAHTOA. What uses adjacent and hypotenuse? Cosine. Good Lord. Okay. Cosine of 35 equals the adjacent, which is going to be the absolute value of x, over the hypotenuse, which is 400. Plus, we're using sides of triangles. Like we're working this as a triangle, and the side lengths are going to be positive anyway. So the absolute value of x is 400 times the cosine of 35. That's going to give me my horizontal component. When you type that in, you get 327.661 newtons. Okay? Let's find my vertical component. That's y. That's the opposite side. So what uses opposite and hypotenuse? Sine. So the sine of 35 is equal to the absolute value of y over 400. So that's equal to 400 times the sine of 35. So my vertical component, once you type that in, I'll just give it to you. I know you can push those buttons. It is 229.431 newtons. This is very similar to what we just did, right? This is your x component, this is your y component. mg cosine theta, mg sine theta. If you're in physics, that's what that is. It's the magnitude times the cosine and sine of the angles. Okay? But we're just splitting them into horizontal and vertical components, and then you decide if it's positive or negative or whatever. Okay? We good? Easy enough? Awesome. So your assignment is informative. I'm going to give that to you right now.